Okay guys, so welcome to our second video on limits, and hopefully you enjoyed the previous one. So today we're going to look at limits at infinity. All right, very interesting, and we may have seen these already, what I would like to call asymptotic behavior of functions when you looked at functions like, for example, the hyperbola. And as x gets very large, what actually happens to the function f of x, for example, 1 over x. You may have also seen this, for example, in exponential functions, so the exponential decay functions like e to the minus x as x approaches infinity. So this is basically what we're going to be focusing on this morning, and you remember infinity, right? Sort of 8 that has just fallen over maybe. So that's basically it. So let's have a look at how we handle when things start to become unbounded. That might be a nice word for us to think about. So just remind ourselves, I mentioned this yesterday, right? The Man Who Knew Infinity, a beautiful book that you see on the top left corner. If you can get a copy and read that, that makes great reading. Or, well, some would choose to watch the movie. I think this is a Netflix, The Man Who Knew Infinity. It's about our great mathematician and the genius Ramanujan, Srinivasa Ramanujan, prolific mathematician, great discoveries, and has really advanced mathematics with these thoughts, these theorems, and his discoveries. So worth a watch, worth a read. So please, yeah, if you can, that'll be very, very just increasing your knowledge as well. I think that'll be beautiful. So let's see, limits at infinity. So I have here Newtonian gravity, right? You see this basically, we've all seen this universal theory of gravitation, classical theory I need to add as well. And if you look at it, it goes like 1 over r squared, or in this case they write here 1 over d squared. So it's an inverse square law. So basically the question is, as r approaches 0, as d approaches 0, so if you've got two objects and you notice that the distance, or the separation distance, sort of decreases, becomes smaller and smaller and smaller as they approach each other, then how does one look at the force? So if you had to sketch this thing, you sort of a rough sketch, and if you got, say, the force over there as a function of d or r, okay, then you should expect some sort of behavior like that. So you notice for a very large d, you get a drop-off in the gravitational interaction between the two bodies. But as r decreases, the distance between the two objects, the centers become smaller and smaller and smaller, you find that the force increases. But here it's quite interesting, isn't it? And that is the d, or the separation distance, cannot be 0 unless the two centers of the objects coincide. So here, while mathematically we can speak of r approaching 0, but in a physics sense or physical sense, you'd find that the centers of the two objects need to coincide. We look at spherical symmetry, for example, this is the simplest case, for r to become 0 or d to be 0. All right. And then something else, I'm just trying to give you an idea of why limits at infinity are important. So for example, if you look at an unstable nucleus, uranium-238, here we also have a very large nucleus releasing a alpha particle, which is 2 protons and 2 neutrons. Then basically, as you look at the decay, say for example, I start off with 100 grams of a certain substance, and then I ask myself, right, an hour later, how much of that material would I have left if it undergoes, say, alpha decay, beta decay, or gamma decay? And you find it's a very interesting law that comes about, and one speaks of what we call the half-life. But one could actually write down, if you look at the number of particles at any present or any given time, right? It's a function of time. It depends on the initial number that you had, and that could be in terms of mass, if you count it. And then it goes like e to, say, the minus lambda t, where lambda is a decay constant. So if you have a look here, it'll be interesting to note as t becomes larger and larger and larger, in the limit as t approaches infinity, what actually happens to this number m, which is basically looking at the mass or the number of radioactive nuclei we have. But as t becomes larger, we'd expect a drop-off, which you can see as an exponential decay curve. So again, very important. So if I get to the mathematics, just as we said, an informal definition, the limit as x tends to plus infinity of a function f of x is equal to L, if you look at equation 3 here, and then 4 at minus infinity. Two simple examples that we've all seen in school. If you look at the top curve there, this is y equal to 1 over x, right? We're familiar with this graph here. It's a hyperbola. It's not even shifted left or right, which means what we have here is as x tends to, now if you have a look at infinity, positive infinity, you'd find that the graph sort of tends towards the x-axis, which basically tends towards 0. And then as x tends to minus infinity, right, if you have a look at this end over here, as x gets larger, it approaches 0 as well. So you can write off here quite nicely, as x approaches minus infinity or plus infinity, the graph of 1 over x, the limit of 1 over x as x approaches plus or minus infinity is 0. Okay. So we've also spoke about asymptotes in school, and if you remember, for example, if you took a function like y equals to 2 to the power x, and we basically wrote something like y equals to 2 to the power x, and we know what that graph looks like. That's pretty straightforward. We could draw that quite easily. We know that sort of does that sort of thing. Yeah, the colors are really bad. So it intersects at 1, right? There's your y-axis, there's your x-axis. And so as x tends to infinity, gets larger and larger and larger, you find that the function becomes unbounded and just increases. But on the other side, as x tends to minus infinity, the function sort of gets smaller and smaller and smaller, and it's asymptotic to the x-axis. So now let's think about a function like y equals to 2 to the power x, sorry, 2 to the power x. I meant 2 to the power x plus 1, right? So it's that blue curve that I've just drawn, but we've shifted that 1 unit up. And you realize that if you look at the limit, now you can sketch this curve of this function 2 to the power x plus 1 as x, say, tends to minus infinity. And because this curve is shifted 1 unit up, this function will tend to, because this guy is going to go to 0, 2 to the minus infinity, so it's going to shift. So y equals to 1 becomes the horizontal asymptote of this function, y equals to 2 to the power x plus 1. Okay, we'll look at more examples as we go along. So what about a constant function as x tends to plus or minus infinity? It's just, so if it's a constant function, y equals to k, y equals to 3, y equals to minus 1, you'd find in the limit, that limit of k, where k being a constant, as x approaches plus or minus infinity would be that constant k, right? So there's no oscillations above or below the function just straight, beautiful, smooth, continuous. So that's quite easy. Now let's take a look at these. When we look at x to the power n. This is quite interesting in the sense that we looked at the derivative. The first thing we looked at when it came to derivatives when we were at school, we looked at the power law. The ddx of x to the power n is equal to nx to the power n minus 1. But now let's just look at the limit here. When n becomes unbounded. So we started off n equal to 1, it's linear, so that's x. So the limit of x as x tends to infinity, right? Linear, that means think of the graph y equal to x, but as x becomes very large, you'd find this function discontinues. Then if you take n equal to 2, we get our famous parabola. And as x tends to plus infinity or minus infinity, so if you have a look here, the limits are the graph that shoots off to infinity, and that famous cubic that we were talking about, right? N equal to 3, you'd find you have this beautiful S-shaped graph. We spoke about the inflection points in school when you studied calculus. But as x approaches plus infinity, the graph shoots off to positive infinity. It's unbounded in the positive sense. And then when it shoots off to minus infinity, if you look down here, it goes all the way there. But y equal to x to the power 4, here we go. This is what we would call an even function. You notice that as x approaches plus infinity or x approaches minus infinity, we see that it sort of this shoots up to positive infinity. So quite nice. It's quite, I like the pictures as well. So it just gives us a feel for this unboundedness when you look at the limits as they approach positive infinity or negative infinity, or what we would call the asymptotic behavior of these functions. Cool. Okay, guys, so far so good, but I just want to have a look here and see. We've just been writing a paper on the effect of higher dimensions. We're looking at star collapsing, but the effect of dimensions more than 4. And for example, just to give you an idea, when you look at asymptotic limits or limits at infinity, here's a really nice simple example. We're looking at the surface density of a star. So if you think of the star as a spherical object and we're looking at the density at the surface, you'll notice that it actually depends on the dimension of space-time for this particular calculation. And I've got a plot over there, and you could see its density, which is the surface density, as a function of time. So the question then we ask is, as time progresses and as the collapse progresses, what actually happens with the surface density? So if you look at each of the color codings there, if you look at the blue, this is n equal to 2, which means it corresponds to 4-dimensional space-time, which is basically our universe. But then as you increase the dimensions, as you go to higher dimensions, you notice that the density actually increases with the space-time dimension. But also what's interesting is you'd find the asymptotic limit is sort of basically becoming larger and larger and larger for late times. So one has to then investigate and ask the question, as the star collapses, right, would it evaporate from our universe altogether when the rate of collapse is equal to the rate of emission, energy emission? And or would it form a black hole? That's something very interesting as well. So I thought let's give it a bit of a sort of an edge rather than this say what actually happens when x tends to infinity, x tends to minus infinity. It's nice to sort of look at some sort of application to these things, even if it's a theoretical or what we call a toy model as well. Okay, so now let's look at limits of rational functions. In this case, where x tends to plus or minus infinity, and we're looking at functions of the form p of x over q of x. So let's just take a quick look at that. And these are interesting even with regards to exam. So here we have a function. So it's 3x squared minus x minus 2 all over 5x squared plus 4x plus 1. And we always said direct substitution leads to infinity over infinity. So we have this sort of situation over here. And then we realize we've got to sort of look at something slightly more different. And if you look here, the leading power of x here is 2, and then in the denominator. So the question then is, what would happen if I just basically divided top and bottom? And I'm going to do this slowly because some of you might be seeing this for the first time. And then we're just going to go like this. Generally, we don't do that. I'll show you what I mean by that just now. And this is 5x squared over x squared plus 4x over x squared plus 1 over x squared as x tends to infinity. And what you'll notice then is the limit, just for illustration here, is 3 minus 1 over x minus 2 over x squared, right? Please check that. And that's 5 plus 4 over x plus 1 over x squared as x tends to infinity. Now, it's interesting to note that that's just a constant. That's a constant. But this, as x tends to infinity, that's going to tend to 0. As x tends to infinity, that's going to tend to 0. Same here and same here. So the final answer is going to be 3 over 5. Agreed? Let's double check that. And you would see that is indeed the case. All right, so you look at the leading terms, top and bottom, and then divide by that leading term. And similar situation over here, 3x plus 5 over 6x minus 8. And you can see it has form infinity over infinity, which is not 1, by the way. And so we could write this as the limit And now if I divide, so I'm going to get a 3 plus 5 over x in the numerator. Please check the 6 minus 8 over x in the denominator. As x tends to infinity, look at my infinity signs. The answer turns out to be 3 over 6, because this guy tends to 0, that guy tends to 0, and the answer turns out to be a half. So you can have a look at that. You can even plot that function, have a look, and confirm that the asymptotic behavior there as x tends to infinity is 1 over 2. Okay, great. So what about this one? Find the horizontal and vertical asymptotes of the graph of the function. Horizontal and vertical asymptotes of the graph of the function. Now, if I just look at, say, for example, the vertical asymptote, let's start over there, right? Something that's pretty straightforward here. We see there's an issue that we're going to encounter, vertical asymptote. If you look here, so if I go 3x minus 5 equals to 0, we know the function sort of blows up at x equal to 5 over 3. So we know there's going to be a vertical asymptote over there, but we need to look at what's really happening as we approach 5 over 3 from the left and also 5 over 3 from the right. So what does the function do? Does it shoot off to infinity? Does it shoot off to minus infinity? Now, do not confuse the behavior of the function when I say shooting off to infinity or minus infinity versus as x tends to infinity or minus infinity. They are two different things, okay? So one is the behavior actual function, and the other one is where we basically oscillating, we varying the sort of x value in terms of them becoming unbounded, right? And then seeing the result of that in the behavior of the function. So if I had to write down the limit, now watch this, of f of x as x tends to say to infinity of this guy, root of 2x squared plus 1 all over 3x minus 5. If I do a direct substitution, I'm getting infinity over infinity. But would you agree with me that if I pulled out an x squared in the numerator, I would end up with an x, and then I'm going to go 2 plus 1 over x squared, right, all over 3x minus 5. I'm not sure whether you see that. Sorry, I should have put down here. You see, that's being naughty. The limit as x tends to infinity, x approaches infinity. So then the question is, if I divide top and bottom by x, what do I get? So I'm going to end up with, let me write this properly now, guys. This is important that you be precise. And so if I divide top and bottom by x, top and bottom by x, the x at the top would go away. So I'm going to end up with 2 plus 1 over x squared. And if I divide the bottom, I'm going to end up with 3 minus 5 over x. So you'll notice anything involving the x in the denominator here now, that's going to vanish, that's going to go to 0. So what I'm going to end up with then is root 2 over 3. Does that make sense, everybody? All right, so for x, now it's interesting because then you'd ask yourself, what I did was I pulled out an x squared, right? And I took the square root of x. So basically I'm looking here, the square root, just a reminder, and remember that's plus or minus x. So there should be another arm or another limit where we're going to take the case where the square root of x squared is going to be minus x, and what we would expect to see is a minus x over there. So the first one, if you look as x tends to infinity, is root 2 over 3. That becomes the horizontal asymptote of this function, right? So now if I take the other arm, right, or the other branch, should I say, where I'm treating the square root of x squared as minus x, as I pointed out here, that should give us a second horizontal asymptote, which is minus 2 over root 3, and I'd want you to confirm that. That's very, very important. So I have a couple of things going on here, and I think the best way to do this is to basically look at the graph of this function, and you'd understand what I'm talking about. So here's the function itself. And take a look at this, right? Firstly, a couple of things to note, right? The vertical asymptote, as we pointed out, is at x equal to 5 over 3. So when we can easily see right here, the denominator blows up at x equal to 5 over 3. But it turns out that the limit of this function, right, f of x, as x approaches 5 over 3, but from the right turns out to be positive infinity, right? So if you see approaching that way, and then here when you approach from that, it'll be negative infinity, right? I think it's pretty clear that that is the behavior of the function, and I don't think anyone has an issue there. 5 over 3 from the left, right, which is here. You clearly see the object, the function, the blue curve is shooting down to minus infinity. Now, what about those horizontal asymptotes? I showed you how we derived root 2 over 3, but then I said there's an existence of a second horizontal asymptote, which is minus root 2 over 3, where it comes from, instead of you're taking the x squared out, you're taking the x squared out as a common factor here, but we're taking the root of x squared to be minus x. And that should bring in quite nicely the second horizontal asymptote, which is y equal to minus root 2 upon 3. Please verify that. What about this one? Root of x squared plus 1 minus x. Now, if you just plug in infinity there, you've got something like infinity minus infinity. Infinity minus infinity, please, is not 0. So what can we do here, right? Like I said, this is not the way to do it. So we basically, and I think you'd know this, we discussed something like this yesterday as well. So we basically rationalize, and as x tends to infinity, and then we're going to multiply, but also let's make use of proper brackets. So this would be root of x squared plus 1 plus x all over root of x squared plus 1 plus x. And hopefully we have not forgotten that what we see in the numerator is a minus b into a plus b. So that turns out to be aibo. Let's get that away there. So that turns out to be x squared plus 1. Don't forget we got to square that, so that becomes x squared. And then in the denominator, what do we have? Remember, this is all over 1. And so we're going to have x squared plus 1 plus x. So that goes away, that goes away. And then essentially what we have is the limit as x tends to infinity of 1 over root of x squared plus 1 plus x. Now you'd notice that as x tends to infinity, what happens to the denominator? As it gets larger and becomes unbounded, you'd find that this function, this limit would tend to 0. Right, easy peasy, not too difficult. And you can see that here with the sketch. So as we approach infinity, right, then you'd find that the function tends to 0. Nice. Okay, what happens here? Now we've got something like find the limit of x squared minus x as x tends to infinity. Now with a direct substitution, you got something like infinity minus infinity. Sort of not good to say that that is 0 or infinity, right? But what we can do is not possibly, but we can write this as the limit of x into x minus 1 as x tends to infinity. Think of the graph of y equals to x. Boom, it goes to the origin, right? Positive gradient. And we notice that as x gets large, then we know that f of x or y equal to x becomes unbounded, goes to infinity. Now look at the function y equal to x minus 1. It's y equal to x drops 1 unit, and basically it's a straight line as well. It's linear, but becomes unbounded as x goes to infinity. So we got a product of two functions, right? So 1x, right, blows up, goes to infinity. X minus 1 also goes to infinity. So the product there we can easily say is infinity. And that's sort of makes more mathematical sense rather than just say infinity minus infinity is zero. That's not the case. Or infinity minus infinity is infinity. All right. So learn to speak mathematics. So guys, we always say this. Hopefully you enjoyed this video. It was enlightening in the sense that we're now looking at when a function becomes unbounded for large values of x, plus infinity minus infinity, which is what we call asymptotic behavior. I've demonstrated that, you have lots of applications in physics, in engineering, in mathematical biology, not only mathematical biology, in biology, and various physical processes. So I think it's important that we study limits at infinity, right? Again, I'd like to appeal to you, and it's interesting that if you liked the video, enjoyed it, please subscribe, please like, also comment. We would very much appreciate your feedback. So yeah, so do not forget to subscribe, and thank you so much for actually watching. And I always give thanks and acknowledge, sources of information together with problems and the graphs. So here we're looking at, say, for example, as I mentioned to you in the previous video, two excellent sources, Stewart Calculus, together with Anton Bivens and Davis Calculus 10th edition, where I've basically consulted, even lifted some of the figures because they were beautiful. And yeah, and really illustrative of what we're trying to say or trying for you to understand, rather than just bring out a whole bunch of formulae. It's always nice to see things and to get a feel for the behavior, and I think that's important. So thanks to the authors, to the editors, and people that contributed to these beautiful books, and everything else on the internet, especially those animations that we use as well. That just makes the presentation dynamic, more appealing, and more exciting. So guys, thank you, and let's wait for the next video. All right, take care.